Resi Kausik, and he worked in Solar Energy Institute in Anand, and he worked as what you call it, and having a professor and HOD at Rajiv Gandhi Institute of Technology in Nandyal, I think I'm right. Now, last 3 years back, he's holding the charge as a director technical and solar thermal division. It is an honor to us be on board with us today and like to deliver on the topics of hydrogen economics. So, with this note, I like to hand over the session to Dr. P. SivaReddy. Uh, Regarding this reflective journal, so 7:30 we can discuss in my presentations. Now over to Dr. C.V. Sivareddy. Dr. Shivareddy, it's Dr. Shiva. Network Center make Dr. Sivareddy a co-host.
Already made, sir.
Okay, okay. Dr. Shiva, your mic is muted. So unmute it.
Okay. Now my voice is audible, sir?
Yeah, it's audible, audible.
Okay, sir. Thank you, sir. I will share my. Yes. I think good evening, sir.
It's a good evening.
Yeah, good evening. Thank you. Okay. Just I will introduce at my current institution, the National Institute of Solar Energy. Many persons knows this is the one of the only one institute working on only on solar energy under Ministry of New Renewable Energy. Here our targets are research and development, design development of technologies for various applications. Second part, testing and certification, standardization, and supporting policy making, MNRE, whatever the policies are coming, the background work of the policy making. And last but not least, the final target is human resource development activity. It's a big challenge because any new technologies we are introducing means trained manpower. That is main important area. So we are supporting these activities. These are the overall activities: solar thermal division, skill development division, hydrogen and fuel cell division, solar resource assessment and solar photovoltaic division and consultancy. And laboratories also we have well established laboratories for latest based on the latest standards. PV module, entire PV module testing is there, inverter, battery, PV lighting system is there, solar water pumping system is there, radiation and testing and solar thermal systems for solar refrigeration technology testing facilities also available. Coming to today's our topic, already I think last 4 days discussed about hydrogen. Then why we are moving to the hydrogen? That's the first one. Hydrogen and green hydrogen. The target is to move to the green hydrogen, not hydrogen. We know we are the third largest emitter of CO2. In that, the major contribution is electricity, whatever the electrical energy we are consuming for our day-to-day life. And next one is industry sector. So these two sectors are targeted for producing more CO2. The estimated CO2 at the standard 2020, I think, estimation 2.6 gigatons per annum. This much of CO2. Already we kept net zero target 2050 and all. The ministry policy, So just scenario, why we want to move hydrogen? That is our pollution. We know one is electrical, second is industry. In the electrical sector, the latest trends, the total manufacture, the electrical production installation cost is 441 gigawatt installed capacity is there. In that renewable energy, we reached 43%. But the total demand utilization not crossed 20%. Installation capacity 43%. We all know renewable energy intermediate. We can't predict. It is not continuous. Still, even though our installation renewable energy installation capacity we reached 43%, but still we are depending upon the fossil fuel sector only. 243 gigawatt only the supporting entire grid stability.
Dr. SivaReddy, sorry
Sir.
for the disturbance. So there is a hide option that you can minimize it. The people are putting chat box. Hide, minimize it.
Where, sir?
Hide. There is in the bottom line, top sharing, hide. So they're saying content is not visible. Come down. There is a hiding that line.
Stop.
After that you can. Yeah.
Okay.
Now people are. Is it okay? Everybody? Yeah. Thank you.
Okay. Now it is visible, sir.
Visible now. It's
Ah,
clear.
okay. So to support fully fossil fuel based electrical generation, we have to reduce. That is our target. For that, the major hurdle, major constraint is storage. How we will store solar energy? Suppose solar energy now winter session only 5 to 6 hours only solar day it will come, and rainy season the intensity availability is low. At that time, again, we want to depend upon the thermal power plant. Means the thermal power plant under low load factors, sometimes it will work. High load factor, it will work. Then cost disturbances will come into the picture. So fully, we want to reduce the fossil fuel utilization. I am using the word reduce. We can't zero. How we can move? First, one option already majority of the persons knows. Pumped storage projects are running, especially in where the river basins are there. Their pumped storage projects are running, but it is not giving the full solution. Our targets, this is the Indian government, Ministry of Renewable Energy targets. Up to 2030, 500 gigawatt of renewable energy installations we have to reach. At present, 190 gigawatt. So almost 300 gigawatt we want to reach. In that solar itself, 280 gigawatt, and wind 140 gigawatt, and other sources 80 gigawatt. Here storage is important. So one of the best option is hydrogen. Whatever the electrical energy we are generating by the renewable energy, intermediate nature renewable energy, we can store, we can produce hydrogen. Then hydrogen can store wherever the seasonal utilization, wherever the grid stability is required, there we can utilize. So hydrogen is one of the solution for storing of the energy. This is one of the target for the electrical energy. Next, industrial sector. Everywhere industrial sector, CO2 fossil fuels we are using everywhere. But some of the targeted sectors, especially the fertilizer sector, urea, fertilizer, manufacturing sectors, they're almost importing 5 million metric tons of ammonia. For urea, 10 million metric tons we are importing, and 3 million metric tons. Total, our annual import value is reaching 6 billions. If we are capable to produce hydrogen, green hydrogen, we can reduce the CO2 emissions. Our target, net zero target, we want to reach 2070. These two sectors, we have to reduce the utilization of the fossil fuels. So best utilization, hydrogen utilization in the Fertilizer sector. Next, oil refineries and steel processing industry. Majorly, we are using the hydrogen. So, in these two sectors, whatever the hydrogen one sector, we are introducing hydrogen for storing of the electrical energy. Second sector, already hydrogen they are using for production of ammonia for different purposes. There we are capable to substitute the gray hydrogen or blue hydrogen by the green hydrogen. We can reduce the CO2 emissions. So demand is fixed, enough demand. I am not touching the automobile sector. That is a very, very minute sector. Our fully concentrated big sector, because heavy demand is there, then only cost reductions will come into the picture. This is the global hydrogen consumption, just some countries, how they are consuming. And sector wise, where the hydrogen we can use, chemical, I already mentioned ammonia production, and iron and steel, and refineries, they are utilizing the hydrogen. And at present, whatever the hydrogen they are using, how they are producing means, majoritarily they are producing 60%, they are producing by the fossil fuels only. Carbon, CO2, CO2 by CO2 sequestration, they are producing 18%. Electrolyzer, like green hydrogen, they are producing only 1%. Then coming to the renewable energy inputs, the scope of renewable energy, only two sectors of renewable energy is fulfilling our needs. One is wind energy. Earlier, wind energy 100-meter height, I think that is around 400 gigawatt target only. Now, the potential estimated by National Institute of Wind Energy, the height is increased to 120-meter. What is the maximum potential capacity? And height is increased to 150 meters. What is the potential capacity? So wind also have the high support, will give the electrical energy generation. Second one, solar. 3 to 5% of the solar energy you are capable to utilize. Also, it will sufficient to fulfill our entire needs. And compared to technology upgradation, because PV panel technology upgradation, when we started a renewable energy side deviation in 2007, I think, at that time, the PV module cell structure can convert the visible radiations only. Now, that range also increased up to 1000. That's why cell efficiency is increased. So absorption rate is increased, automatically output also increased. Earlier, the efficiency, the laboratory efficiency is coming only 15%. Now it is crossed to 23 to 24%. Field efficiency also, majorly we will get 18 to 20%. So these are the renewable energy technologies are available. Two technologies to substitute the electrical and industrial needs. By using the technology, how best we can produce the cost-effective way we can produce the hydrogen. I am not discussing about the what is the hydrogen value, because already for last 4 days you are discussing this one only. Just I am comparing this, what methods we are producing the hydrogen, what is the CO2 emissions. The brown hydrogen, brown coal gasification, the CO2 emissions per kg of hydrogen, black coal and gray hydrogen, natural gas with carbon capture. This is the CO2 emissions. You can see here I mentioned green hydrogen also, some CO2 emissions I mentioned. One word we are using green hydrogen. By using renewable energy, we are producing electrical energy. Same electrical energy I am using for production of hydrogen. Then also I am placing 0.9 kg of the hydrogen, CO2 we can produce, can generate for the production of hydrogen. This is true, but how we are calculating this one means, by using solar PV panel, whatever the electrical energy you are producing, there is no CO2 production. But the processing of the module, cell, wafer, backsheet, highly energy consuming technologies. So based on the technology per kilowatt and the lifespan of the module, the estimation value of the CO2 production is 40 to 50 grams per kilowatt hour. So that much of the CO2 averagely, indirectly we are producing for manufacturing of the product. So manufacturing the product, we are not using the renewable energy. So that's why green hydrogen also some CO2 emissions will there. It can reduce based on the different technology. Now technology upgradation is there, the value is reduced, but the CO2 emissions not zero by the green hydrogen also. This is the technical aspects, almost majority discussed for our economic analysis purpose. Just some of the points I am touching. One is cell pressure. First, alkaline electrolyzer is the best matured electrolyzer system, but the main problem, it is not suitable for the renewable energy. Why? Because renewable energy is an intermediate nature. The responding time, alkaline electrolyzer responding, it will take time, 1 hour, 2 hour, based upon the heater arrangement and pressure enhancement arrangements. It will change. But for continuation operation, if continuously you are getting the grid power, electrical energy, then the cheapest and well matured technology, alkaline electrolyzer, for industrial application they are using, and the the pressure of the gas also, it will produce less pressure, only 1 to 10 bar, and the maturity fully matured, and lifetime of the stacks also, electrolyzer stacks also is high compared to other. Second one, anion exchange membrane. This is it is not fully matured one, R&D stage only. Next, proton exchange membrane. This is also somewhat mature technology. The main advantage, it is well suitable for the intermediate nature. Means responding time is very, very low compared to alkaline electrolyzer. And hydrogen purity. If responding time is very low, the purity also high. Alkaline is a liquid electrolyzer. That's why again purification is required. Here purity is high. And the production pressure also somewhat high, 30 to 50 bar. Means next to storage purpose, some storage cost, somewhat it will reduce by the proton exchange membrane compared to alkaline electrolyzer system. The efficiency is almost equal, both efficiencies. Last one, solid oxide. Solid oxide, where the thermal energy is available, plenty of the thermal energy is available, then free of cost. You are generating thermal energy, there is no use. Free of cost thermal energy is available, and so industrial waste heat. Then electrical energy inputs will reduce, but life of the electrolyzer life is less, but efficiency is high, 80 to 90% efficiency, but thermal energy. So two technologies, especially for our renewable alkaline electrolyzer and proton exchange membrane only at present adopted. Solid oxide, generally industrial waste heat they are considering. So these are the energy input requirements for each technology. Alkaline electrolyzer, roughly 4.5 to 5.5 kilowatt hour electrical energy, it will use 1 meter cube of hydrogen production. Operation conditions I already mentioned. Next to proton exchange membrane, because somewhat less efficiency compared to alkaline electrolyzer. The electrical energy need is 5 to 6.5 kilowatt hour, but the operating pressure is high. It will reduce the storage cost. Solid oxide electrolyzer also I mentioned. Then these are the electrolyzer part. What is the technology, commercially available technologies, and what are the cost economics is fitting. Next one, storage technologies. At present, compressed hydrogen gas, this is one of the mature technology, because in our institute, I will show the photographs. In our institute also filling station is there. we are generating the hydrogen and compressing up to 700 bar and storing 700 bar. And filling stations are there. At discharge pressure is 150 to 200 bar discharge pressure. We are discharging the hydrogen. The compression energy cost, this majority of the cost I mentioned in dollars. Why? Because Indian rupees now also it is not converted. Why? Because mass production rates are not coming to the picture. That's why I kept in dollars only. The compression energy $0.5 to $1 per kg of hydrogen. Next, second technology, liquid hydrogen. Main cryogenic storage. This is a high challenging one. One is reaching to minus 250 degrees storage temperature. That is the first challenge. Second challenge, to maintain the tank temperature also. So proper insulation is required. Otherwise, again, it will convert to gas. Gas means again it will change the volume. It will create big issues. So tank manufacturing of tank and insulation system is main problem. And one more challenge, boiling of losses. Because next hydrogen we are storing, what purpose we are storing? Next we will generate the electrical energy. Then once we want to generate electrical energy by using any method, at least 70 to 80 degrees of temperature is required. Again, that boiling of losses also is coming to the picture for liquid hydrogen storage. Next, metal hydrates. This is one of the R&D subject indirectly, because lower capacity we want to store. Different metal hydrates are there, but I think Department of Energy, US government, they kept the benchmark. Any metal hydrates or battery technology per meter cube or per kg of the volume of the metal can capable to store at least 2.5 units of the energy. That is one of the benchmark target. So different, I think metal hydrates discussed, different metal hydrates, main heavy weight, and charging, discharging also, it's somewhat is not a faster rate. Releasing time it will take, releasing time, but releasing of the hydrogen also you have to spend some energy, means some heating is required. And metal hydrates not fully matured one for industrial application. Whatever the application in my mind is only electrical energy generation. Second one is industrial hydrogen substitution. For these two purposes, metal hydrates not fully supporting technology, but lower capacities where decentralized storage is required, there metal hydrates one of the promising storage methodology. The cost also $15 to $20 per kg of storage. Next, chemical storage. This is the best storage. Why? Because I already mentioned ammonia only we required for fertilizer industry, urea industry. Direct ammonia is required. So you convert ammonia, direct ammonia you can use the industry. This conversion of the ammonia also $0.5 to $0.7 per kg only. But you want to again ammonia to hydrogen for electrical energy generation, means again that reverse condition also, uh, you have to spend some energy. Transport cost is similar to other liquid fuels. Already ammonia transportation methodologies are there, so it is there is no special technology or special features you don't want to concentrate on. The best one at present, Indian government also concentrated, and 5 zones they identified. I think Tamil Nadu one zone, Gujarat one zone, storing in salt clay caves, like rock caves in underground, buried. We are burying the hydrogen when the electrical energy, so solar energy is there. If grid is not required, we are continuously producing hydrogen and we are storing that one. Whenever it is required, we can extract and we can generate the electrical energy. This is the one of the best storage. Like natural gas fields also we are depleting, natural gas also we are storing. Here the storage cost also very low, $0.2 to $1 per kg. Artificially you want to create the infrastructure cost is coming to 10 to $20 million. This is mainly for grid stability in seasonal, like winter, rainy season. Their electrical energy grid required stability. At that time, this type of large amount of the hydrogen we are storing means it will support the grid stability. So one of the best method. And now Indian government also concentrated this one. This is the storage, and storage different technologies costs the involvement of the costs. Next one, transport methods and costs. Which are the best transport methods? Pipeline transportation. If we are blending with natural gas, already natural gas pipeline systems are available, well established in India. So we are capable to use that one. Then what is the cost? Then $1 to $2 per kg of hydrogen. A retrofitting of the natural gas pipelines, 10 to 30% of cost of new pipeline cost it will take, because hydrogen density is very, very low compared to natural gas. For large scale, long term supply to the industry cities, it is the best option. Compressed gas, I already mentioned, filling stations we have. Like filling stations, generally they are compressing the hydrogen and storing the tanks and discharging this one. This is one of the regular storage system. Liquid hydrogen tanks, but I already mentioned liquid hydrogen. Main problem is that boiling of losses are high, but one of the best method only. But this is not cost effective method. High cost consumption, $3 to $5 per kg. But exports, it is good. Next, like ammonia transportation. At present, the best suitable one, hydrogen blending with in the natural gas pipeline. At present, that is only is running. So now, whatever the pilot projects they are giving, Indian government, I will show the Indian government policies also. They are concentrated like that areas on where the system already available. So we can reduce the investment cost for the transportation system. So this is the cost comparison of the table, the compressed gas, liquefied gas, metal hydrates, chemical storage, underground storage, and pipeline transportation. First, cost reduction strategies, like because the R&D part is coming to the picture. Main storage technologies, material tanks, type 3, type 4 material tanks, cost we have to reduce. Next, optimize the transportation logistics, pipeline integration, levelize renewable energy for compression and liquefaction, and regional collaboration for sharing of the infrastructure. That is the main important. Then only already existing system you are capable to utilize. We can reduce the entire total production cost of the hydrogen. So these are the storage systems. First one, electrolyzers. Next, storage. Next, transportation. These three are the involving costs of the hydrogen plant, hydrogen plant. Coming to our economic evolution, CapEx, OpEx, generally word we are using. CapEx means capital expenditure. The capital expenditure for green hydrogen only we are discussing. Electrolyzer system, different based on different technology, the cost is varying. And renewable energy cost also. If you are using solar PV panel, if thin film cells you are using, one cost it will come to the picture. You are using PERC system or heterojunction system, or you are using wind energy. So based on the renewable energy cost, the cost variation per kilowatt will change. Next, storage and distribution. These also large capacity caves you are storing, then storage cost is low. Or you are just high pressure, like your 30 bar pressure, you are producing hydrogen and you are transporting to the industry directly. Then their storage and distribution cost also will reduce by using the existed natural gas pipelines, retrofitted natural gas pipelines. Next, balance of the power plant and construction approximately estimated is 30 to 50% of the total electrolyzer cost. So this is the capital cost of the total green hydrogen production system. Coming to the operation and maintenance, regular maintenance of the electrolyzers and all, the estimated 2 to 4% of the electrolyzer cost is coming to the picture of for the maintenance. But the major maintenance cost is energy input only. This is approximately based on the technology. It may be alkaline, it may be proton exchange membrane, because these two only at present green hydrogen they are using. 50 to 55 kilowatt hour energy we have to use for the production of the hydrogen. So the major operation maintenance cost is energy input cost. Next, water cost. Electrolyzer required high purity water. 1 kilogram of hydrogen approximately production it is required 9 to 10 liters of the water. So contribution of the to the overall hydrogen cost, the energy input and maintenance cost and water cost. Current cost for the green hydrogen based on the why, because electrolyzers in-house manufacturing now initiated, so importing stacks are importing, the materials also costly, and minimum the importing also less quantity, the quantum is not increased. In this condition at present the green hydrogen production cost is estimated $3 to $8 per kilogram. But one of the best achievement at present, in 2007, electrical energy by PV panel, the unit electrical energy cost is 14 to 16 rupees. Yet present, without any subsidies, I think Adani and different companies, not Adani name I am giving, because so many governments that have the including transport, interstate transportation also, the unit cost at present is 2 rupees 49 paise. Wind energy also like that only, 2 rupees 1 paise. If inside the state they are producing and supplying, means the cost is only 1.9, less than 2 rupees. So the renewable energy cost is drastically reduced from 2007 to 2024. Here we are not changing the silicon. You can observe that one. Why Indian government is confident about green hydrogen also, we can reduce the production cost. From 2007 to 2024, drastically we reduced to 16 rupees to 2 rupees. Simple. One is cell efficiency, cell absorption, solar absorption capacity, wavelength is increased. That's why cell efficiency is increased 15 to 20%. And by the mass production, technology upgradation of the production of the modules, the production cost drastically reduced. In India itself, now 38 gigawatt production capacity available in inside the India for PV panel, PV module manufacturing. Cell manufacturing, 5 gigawatt production capacity is available. That's why cost is reduced drastically. Like that, electrolyzers also, we are capable to produce more, utilize more, and enhance the efficiency. At present, whatever the electrolyzer mature technologies is there, their efficiency is low compared to solid one. The efficiency is enhanced from 60 to 90. Then this mass production is coming to a picture. We can reduce the overall green hydrogen cost $3 to $8, whatever the cost at present running, we can reduce equivalent to the gray hydrogen cost. That is the targeted one. Though that I already mentioned, what are the factors contributing? Electrolyzer is the main contribution. Second one is renewable energy, and electrolyzer in electrolyzer production and efficiency also. Load factor, current efficiency. So these 3 points Indian government concentrated. One is efficiency enhancement of the system. Second one, reduction of the production cost of the electrolyzer. Third one, integration of this renewable and this one storage integration, low cost storage integration. These three are the major factor contributing the reduction of the hydrogen cost. So based on these three parameters, Indian government launched National Green Hydrogen Mission. These are the four targets: exports, domestic demand creation, because these are not demonstrated projects. You can see our website also in MNRE website. These are the not demonstrated, the commercial viable projects we want to initiate. And certification framework we are started. The NICE only the body certification framework body for that green hydrogen mission. So here one of the policies is strategic interventions for the green hydrogen transmission. This is the first strategy. In that, two methods we are concentrating: supporting domestic manufacturing of the electrolyzers. This is our first incentives we are giving, strategic incentives. Second, incentives we are offering production of the green hydrogen. Where the production of the green, I think Tamil Nadu government came forward, and UP government came forward, Maharashtra government and AP government. A total 7 to 8 governments came forward. We will produce the green hydrogen, especially for the utilization of their fertilizer industry. Where which states have the fertilizer manufacturing capacities, there we will substitute the ammonia imports. We can reduce the ammonia imports by production of the green hydrogen. So the two incentive schemes launched for domestic manufacturing of electrolyzers and production of green hydrogen. Pilot projects I already mentioned. Pilot projects properly concentrated, where the storage, where the transportation facility pipeline, already natural gas pipeline facility is available. Their retrofitting is 10 to 30% of cost. With retrofit, we can transport the hydrogen. And storage, the caves storage facility, easily we can acquire. And the renewable energy production capacity also. These are 3 points. Based on 3 points, some pilot projects Indian government is sanctioned and sanctioning up to 2030, their continuation process. And also whatever the figures I am showing, that 400 crores, so 100 crores, these figures continuously will update based on the demand side. Initially, Indian government targeted, initial budget they given 17,490 crores for implementation of the National Green Hydrogen Mission. But based on the project upgradation, the amounts will increase. This is not the end limit. So this mission outlay, the mission outlay, first thing, 5 million metric tons. I already mentioned, only for ammonia production itself, we required 5 million metric tons of the hydrogen to substitute ammonia, industrial agriculture need only. So our target by 2030, we have to produce at least 5 million metric tons of the green hydrogen. And electrolyzers also, electrolyzer production capacity inside domestic, we have to increase. And whatever the 280 gigawatt renewable energy is there for solar, and other total 500 gigawatt, whatever target is there. With that target, again, one more 125 gigawatt special renewable energy projects also for hydrogen production only, separate sanctions they are giving. So overall, by these initiatives, Indian government expecting 8 lakhs crores of investment for this for the mission. But that all one point. The major target is employment. 6 lakhs new green jobs. 6 lakhs new green jobs. In this point, whatever the contribution we are doing, just I will share this one. We know 280 gigawatt solar PV installation is required. Okay, manufacturing, they are doing manufacturing. Then EPC, they want to install. Where is the manpower? Indian government launched Suryamitra program. National Institute of Solar Energy only conducting this Suryamitra program. ITA graduates, diploma graduates, technical trades, ITA diploma graduates. We are training as a solar PV installer from 2015. Till date, we trained 57,000. This year, our target is 12,800 technicians we are training. Already process launched. You can search in Suryamitra plus NICE. You will get the all training centers. If anyone, your students are interested they are interested in green job side, they can enroll. And second, recently Indian government launched. I already mentioned the target is 500 gigawatt plus 125 gigawatt. This much of the installations required. Not only power plant based, decentralized installation also, like PM Suryagar Muft Bijli Yojana. One scheme is launched. The project cost is 75,000 crores. 1 crore homes we have to install the renewable energy, the electrical bill free homes, at least 1 crore. 2027 only our target. So for this decentralized, huge manpower is required. Our estimation manpower is 3 lakh manpower. In the first phase, at present under PM Suryagar, three types of the trainings we are giving for the employmency purpose. One is solar PV installer and supervisors, and whatever the persons who studied related to solar, but they don't have hands-on experience on the field. For that, for them, on-job training also we are giving. Like that, three schemes. Under these three schemes, the first phase, 1,85,000 trained manpower we are creating. In that, 58,000 NICE only contributing this one. This NICE only can't. So any government scheme is coming to the picture. One is funds, second this investments, costs. That one area. Second area, major area is the employmency. So this total employmency target by the green hydrogen, because green hydrogen means renewable energy input is required. Next, electrolyzer. Now hydrogen side also we started the training modules, training plan of action we started for electrolyzer, how the production, storage, safety side. Also we are giving training, but that is a plan of action only. We are not initiated, but regarding solar PV already initiated by NICE. But hydrogen side, different IOCL started, different organizations already started. So this is the overall view of the system. So the major costs, based on the mature technologies, electrolyzer is paying the major cost, and second one is energy input, and third one is storage, fourth one is transportation. So these logistics are properly interlinked, then only we can reduce the levelized cost. So for this only national mission, the phase one, our target creation of the demand, domestic demand. Phase two, export level, we have to enhance our capability. 100 million metric tons our target. Coming to the R&D part. R&D also, you can see our entire policy document. Here, R&D priorities also, strategically we provided R&D priorities. Immediately we required, what we required? Reduce the electrolyzer cost. Then what are the materials we are using, anode side and cathode side? What materials, what catalysts we are using? What are the separators we are using? How we can reduce their cost? So first R&D priority, the existed technology, whatever the challenges, 6 to 5 years research proposals invited. But majority of the proposals, collaboration with the industry. I already mentioned these R&D targets, not demonstration targets. Next one, grand challenge projects. Here, that biomethanation. Not only these two are the mature technologies last 150 years, but other methods also we can produce the hydrogen. So there R&D priorities given. Next, 0 to 15 years. Other methods. One is wastewater to hydrogen. At present, whatever the water we are using, pure water we are using for production of the hydrogen, like seawater to hydrogen, add photoelectrochemical water splitting, very low efficiency at present, the concentrator, that one. The thermochemical water splitting by using solar concentrators, high temperature concentration, and microbiological, because wastewater purification. Our target is purify the wastewater. By the purification, you are capable to produce the hydrogen. Some of the demonstration projects are there, but the efficiency is very, very low. And next, hydrogen storage also, storage materials, main storage tanks, type 3, type 4 tanks, production, and different hydrogen storage methodologies like uh, then these are the targets we kept. Then who are the manufacturers? That is also now I think NTPC came forward. The NTPC will play the big role in this electrolyzer manufacturing. NTPC, L&T, AFC Energy. This is UK based company. Renew, Siemens, IOCL, Tata Group, Switzerland, Greenco Power, Adani. Some other Indian startups also is coming. These are the major players. I think NTPC recently launched that new portfolio also, NTPC Green something, separately for the renewable energy only. So manufacture also available. So whatever the production cost, we are estimating $3 to $8. At present, India means $6 to $8 only. That cost we have to reduce by playing the major role of these Indian manufacturers. This is the system already available in our institute. I think 2012 we established. At that time, 5 meter cube system. The filling station also is there. 5 meter cube per day it can produce, per hour it can produce, not per day, per hour it can produce. This is the storage and filling station. At that time, we kept MOU with the Mahindra for automobile use only. Type 3, Type 4 storage tanks also is there. Now we enhanced that capacity to 15-meter cube. But I already mentioned alkaline electrolyzer we are using. But alkaline electrolyzer major challenge purity and responding time. These two are the major challenge for renewable energy integration. So the future cost production, generally key performance indicators we are considering the levelized cost of hydrogen, $3 to $8 to $1 to $3 means by 2030, and $1 to $2 by 2050 means equivalent to blue hydrogen cost. Our target. So for that energy efficiency, our target to increase the electrolyzers, today's typical energy efficiency is 65 to 75%. We are capable to enhance 80 to 90%, then only we can contribute that. Then carbon emissions reduction, already CO2 emissions reduction by the green hydrogen. That cost also we are helping. The payback period. The large capacity plants or large electrolyzer manufacturing systems are coming to the picture. Then the payback period estimated 5 to 10 years. 5 years is best payback period. At present, the payback period without subsidies, it will not come. It is not fitting to 5 to 10 years. Next, any industry models are coming to the picture. Anywhere the industry models are coming to the picture. The industry models, they are expecting internal rate of returns also. Whatever their investment, earlier I think I mentioned is, is the target 8 lakhs crores of investments we are expecting. Any investor for a social service, they will not invest. So their expected internal rate of returns at least 10%. Because in simply we are keeping in fixed deposits or anywhere, we will get 6 to 8%. More than that they are getting, then only they will come into the this business, at least 10% of the rate of returns. The overall lifetime 10% is, these are the estimated one. For the estimated one, we are expecting like solar PV panel, like this electrolyzers cost also will reduce. The what are the materials we are at present, we were replacing the materials. And separator also, recently I think in Bangalore one industry started with water as a separator. The efficiency is low, but the cost of the electrolyzer cost is reducing automatically. One of the method they are using. So I think this is the, because I'm not concentrated on the technology point of view. Technology already discussed. The economics, where it will fit a total economics part. One is efficiency, mass production, renewable energy input. Then only paybacks are coming. Otherwise, at present, Indian government is giving some incentives. I think in strategic plan of action, we are giving at present, initially up to 2029 to 30, we are giving some incentives to balance that cost. The more than $3, whatever the cost is coming, that cost is substituted by the Indian government to encourage the industry. But in the meanwhile, the cost themselves they have to reduce, like a PV manufacturing. I think these are the systems. So here in our institute, just on our institute plant working, I will explain. This is not a commercial plant. In India, first plant for demonstration purpose, green hydrogen demonstration, established in 2012. One more plant, that proton exchange membrane electrolyzer based plant at IOCL. In Delhi, only two plants are there. So this plant is the first plant. Here, in our institute, I think more than 200 acres land is there. So we have almost 700 kilowatt capacity renewable energy installations are available. So full green energy we are supplying. But the plant running time not 24/7. This is the electrolyzer. This is the purification system. I already mentioned that purification and control unit. This is the compressor unit. This is the storage unit. This is the filling station. And maybe some of the persons may visit also, they can see. Now we increased that 5 meter cube to 15 meter cube. I think I will stop my presentation. We can start discussion. It is good.
Yeah, so
Because economic point of view we are discussing means it will not prolong more concept.
yes, Dr. SivaReddy, then he is very, what do you call it, the policy making process in the government of India, wherein exclusively on a solar thermal system, is in the part of various committee. The participants, if you have any kind of questions, please you can interact with Dr. SivaReddy. He will be in supporting in nature. So over to all the participants.
Sir, good evening, sir. Am I audible?
Yes, sir. Yes, sir. Dr. Ranjan Rao.
Sir, I'm
Yogesh.
Yogesh,
Okay, sir.
Dr. Yogesh. Sir, actually, I have two questions. One is solar thermal. What is the scope in solar thermal in India?
Sir, officially I can't tell. Main problem solar thermal, because my base area is solar thermal only. My
Okay,
publication you can see solar
okay,
concentrated power generation, my PhD area also.
sir.
But beam radiation availability drastically reducing, sir.
Okay,
My cost economic analysis also, when I did in 2012, the unit cost around without any subsidies 12 rupees to 18 rupees is coming. At that time,
Okay.
the beam radiation I expected 700 watt per
Okay.
meter square.
Okay.
But at present, when it is coming to the field in Sperry Sardar Patel Renewable Energy Institute, I demonstrated project I initiated. At that time, 500 also we are not getting the beam radiation.
Okay.
Without beam radiation, we can't. But thermal not for power generation, sir. Thermal we can substitute as a aided solar aided power generation. We all reheating regeneration, technique,
Yes.
the
Yes.
Rankine
Yes.
cycle.
Yes, sir.
Regeneration process we can substitute, sir. My 2-3 publications are there. Now NTPC is proposing, one proposal came for substituting of the regeneration process by using the solar thermal system.
Okay.
You can concentrate in that area. It may address the things because 300 to 500 is not big issue. 300 we
Okay.
can do.
Okay. Because I am from in the south, so a lot of sun rays will be available. That is the reason I asked the question. My second question is, sir. Actually, our institute is autonomous institute,
Okay,
UGC autonomous. So,
sir.
can we have any MOU with NISE for training programs for the students?
Sir, MOE is not required. You can see our website.
Okay.
Continuously we inviting. Every
Okay.
month,
So,
whatever the applications are coming for internship
okay.
purpose, 1 month
Okay.
or 6 months internship purpose, every
Okay.
month we are scrutinizing and we are providing the service for them. Or otherwise, different trainings. One thing I missed that point. One is Surya Mitra, Suryagar, I already mentioned for large India wide. In our institute also, we are running the training programs, sir, for upskilling
Okay.
programs for graduates
Okay.
and above qualified candidates. Different
Okay.
area. You can see our website. Entire schedule
Okay.
is there, sir. For that,
Okay. Thank you,
MOE
sir.
is not required.
MOU is not required, but
Not
is it
required.
possible
Everything
that
is available.
so suppose research person like you or anybody from your institute, we call in our college and we have some program. Can we do that?
Yeah, that is possible. That is possible.
Oh, okay.
You can
Thank you,
you
sir.
can write to DG automatically.
Yes, sir. Yes, we will
Yes.
write to DG and we will
Yes.
get the permission. Thank you.
Yes. Yes. No.
Thank you, sir. Thank you.
Yes.
Any other questions? I think Rangarao, you raised your hand, please. Mr. Rangarao?
Hello, sir. Good evening, sir.
Good evening, sir.
Good evening, sir. Sir, it's very informative. Sir, is there any companies to producing on this one, sir, using these technologies, thermo,
I think
solar PV thermo electrical system, sir? And also I want to know like a policies, sir. Is there any policies
sir,
for this?
that's why hydrogen. That's why in presentation also 3 to 4 slides I mentioned green hydrogen policy, national green hydrogen policy. You can download in a MNRE website is there, sir. Detailed policy is there for strategic implementation. Up to 15 years plan of action is there, sir.
What about the commercial aspect, sir?
Commercial, I mentioned, no, sir. One is electrolyzer manufacturers. Any manufacturers are coming for domestic production and material substitution. Whatever the materials we are using, costly materials. That's why electrolyzer cost is high. 60% of the plant cost is electrolyzer cost only.
Thank you.
NTPC, I already mentioned. Big player is NTPC. At present came forward. That's why they raised the fund from the public also recently. And Adani already is there. And UK and UK based 2-3 companies are there, sir. Recently, Green Hydrogen International Conference, one conference we organized. That conference details also you can see there. Whatever the companies are participated in Bangalore based 2-3 companies are there, sir. They are not on the point of this alkaline or proton exchange membrane. Different technologies, but that is not commercially viable. But they initiated the work.
Thank you, sir.
There is one Dr. Trijo, he put some chart box questions. If Dr. Tirjo is available, please you can ask your question to the expert, please. Dr. Tirjo, his question is, can I read, Dr. Reddy?
Yes, sir. Yes, sir.
I have mechanical engineering background. I want to do the start research in green hydrogens. Where should I start?
Electrolyzer material side, they can start, or storage side, they can start.
Okay, okay,
These
okay.
two areas are very good areas.
So having in potential, right?
Yes,
Great
sir. Yes, sir.
potential, yes. On green hydrogen aspect is
Yes,
concerned.
yes. Recently, we called the proposals also from different parties, especially for testing and standardization. I think we received more than 45 applications from government and private. We are scrutinizing that one.
Okay. Very good, very good.
Yes.
The participants, please keep it in your mind. Our Dr. Reddy is in the various committee, even in scrutinizing also. Please, you can interact with him.
That's why I shown the policy. Anyone
Yes, 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 yes.
download the policy, you read yourself where you are fitting, then you concentrate and prepare the proposal, submit to the MNRE.
I think if there's no questions,
Hello, sir.
yeah,
Sir.
please.
Sir, you have used that alkaline water electrolysis for producing 5 normal meter cube per kg hydrogen, right?
Yes, sir.
So in that, how much time it took for startup time?
Startup time without heater means it is taking 1.5 hour to 2 hours, sir. Because the electrolyzer operating temperature is 80 degrees. If
Oh,
you connect the heater, then the responding time, including the purity, less than 1 hour at present.
okay. It is run by using battery or by directly by integrating with the solar.
Integrated solar only, sir. Integrated solar.
Okay. So in both,
Stabilization, we will do the stabilization, that is secondary.
uh,
Stabilization is required, but purely by solar energy only.
okay. So any difference will be there in startup time if you use battery or directly
Sir,
from solar
startup time mainly it is the main problem of the temperature, sir.
temperature?
By
Okay.
battery or by grid, whatever the way you are giving electrical energy, but they
Okay.
want continuation power, not intermediate power. That is only
Okay.
the point.
Okay. 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 Thank you, sir.
Okay. Dr. Shiva, I have, you got done a good presentation. I have one question. No, other participants, if you have question, please. Dr. Suresh also is here. Yes, if somebody want to ask questions, please you can ask.
Yes, sir. Just one more question from my side. Here, Dr. Tirupati. So I think
Sir.
Yes, yes, please proceed, Tirupati.
the India is looking for the only electrolyzer manufacturing most of that. Maybe if you see the electrolyzer manufacturing bucket list,
Yes, sir.
almost more than 90% is the alkaline. Then what is the reason behind that, sir?
Sir, alkaline, at present, alkaline for large capacity, stack life is high, 60,000 hours. In my presentation also I shown. Proton exchange membrane at present life is 30,000 hours. One is
But,
first thing.
but PEM is more flexible for intermittency of RE.
Yeah, I would. For renewable energy intervention, FEM is more flexible, but cost is high. The efficiency PEM efficiency also, so compared to alkaline, somewhat low. I already mentioned 4.5 to 5 kilowatt hour for alkaline. For FEM, 5.5 to 5.5 means 1 unit difference is there per meter cube of hydrogen electrical energy input. One is input, because operation maintenance cost is only depend upon the energy input. Second, the life of the stack. At present, the materials, why? Because main that proton exchange membrane only one company only producing. That's why the cost is too high. Now, Indian government concentrated on both technologies, sir, not one technology. IOCL in FEM only. Only NICE initially they installed this one because fully mature technology. At that time, 2012, not now.
But PEM is, what I heard is the PEM is more efficient compared to alkaline. And recently we have
More
visited
efficient in the point of the purity.
pu- purity.
Alkaline again separate purification system you have to arrange. Otherwise, the purity is very low.
Yes, sir. The main difference is alkaline, the only stack they will supply, and the balance of the plant we need to arrange.
Yes, yes, yes,
And but coming to PEM and the BOP and everything is inbuilt.
yes, yes, yes.
Yeah,
Yes.
recently we have visited the Omium electrolyzer manufacturing company in Bangalore.
Ah, yes, yes.
So they have mentioned that it is the efficient compared to alkaline, and the cost is also, it's 1 crore per megawatt is the only variation in between alkaline and PEM.
Hmm.
So
Stack life.
the stack life they have guaranteed the value is 60,000 hours.
For alkaline, not FEM.
No, that was PEM, sir, actually.
Okay, very good. The maturity is coming automatically. The persons at present for renewable energy, majority interested in FEM only because the responding time is very, very low compared to alkaline.
Yeah, the ramp up rate is also, it's around 10% to 100% flexible.
Yes, 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 yes. No doubt, no doubt. We are facing that problem, especially as an institute. We can't run 24/7.
Yeah. Then one more thing I wanted to ask, sir. Can you suggest the alkaline electrolyzer daily start and stop? Let us say I have the
No,
only
no, no,
energy input
no,
is.
no, 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 no. It is not appreciable. 1 hour you are wasting the energy input.
Yes, yes.
This is the loss, no, sir. 1 hour electrical input is loss. 5 meter cube means 50 into 5. That means the electrical units you are wasting.
Okay, fine, sir. Thank you.
Yes, yes.
Good evening, sir.
Good evening, madam.
Um, I'm Anushka Kulkarni. I'm a research scholar at VJTI Mumbai.
Yes,
And
madam.
I wanted to know how we can say that ammonia producing units are the most carbon emitting
Yes.
sections of the industry, because the carbon that they produce, see, what I have come across is that whatever ammonia production companies are available, they end up making urea. So for making urea, they use the carbon dioxide that is produced in their own company. So if the carbon is getting reused and we need urea, how can we say that they are producing carbon?
At present, ammonia they are not producing. I think Tamil Nadu persons knows, any participant from Tamil Nadu. Toothukudi, the Bay of Munnar they are calling. There we are importing ammonia. For production of the ammonia, hydrogen is required. That hydrogen they are producing
Yes,
by
sir.
the gasification.
Yes, sir.
That's why I already mentioned one example also I given. Solar PV panel, by using solar PV panel, we are not producing CO2. But
But
the
sir,
manufacturing of the
the
panel, whatever the energy inputs, what are the materials you are using, per kilowatt hour, at least 40 grams of the CO2 on an average, it is adding. Like that, for ammonia, whatever the ammonia at present we are using, that ammonia is generated or prepared by using gray hydrogen only. By coal or by gasification of the coal or natural gas. Natural gas somewhat good. Coal means high hydrogen, like 100 to 200 grams per kg of 1 kilowatt hour of the energy production. That is interlinked, madam. Ammonia fertilizer manufacturers not producing any carbon dioxide. No doubt at all. Whatever point you said is true.
okay, so are we saying that the amount of carbon dioxide used by the fertilizer company is way lesser than the amount of carbon dioxide that is produced after gasification? Are we saying that? Uh, I did not
Gasification
come to
not
a
done by
conclusion.
the fertilizer industry. Fertilizer industry not producing hydrogen. First thing, they are
Okay,
utilizing the
so
ammonia.
okay,
That
okay,
ammonia our target is that ammonia also we want to produce by the green hydrogen. Then we can mitigate the CO2 consumption. I already in the imports I already mentioned more than 10 million metric tons per
So
year we are
if again, sir, I'm again at the question where I want to know if we are importing NH3,
yes,
just like you mentioned, why
yes.
can't we take carbon dioxide exactly like we are importing NH3 again from the same company? So what I mean is, if we can recycle the carbon dioxide that is being used, or let's say we can even use the CCUs and then convert, take that carbon dioxide and take it to the fertilizer company. So if we are importing NH3, similarly we can take carbon dioxide, which is anyways going to go waste and into the environment. So it's
So,
just my way of thinking of.
madam, a small question. What is your background, madam? Background means basic degree. I am asking.
Oh, I'm a mechanical
Mechanical?
engineer,
Ah,
sir.
mechanical. Now you know that one. Actually, in the atmosphere, the CO2 percentage is very low.
Yes, yes, sir.
Very, very low.
Hmm.
N2 is high.
Yes, sir.
So CO2 exporting by COT, the caloric value of the COT is low.
Hmm. Yes.
We want to produce hydrogen, carbon hydrogen bonding is required, not CO2.
Okay.
Okay. Different options are there at present. Whatever the commercial is moving, that commercial how best we can substitute. That is our target.
Okay, sir.
That's all.
Okay, sir.
Yes.
Thank you, Mrs. Anushka Kulkarni, ma'am. So I think Tricho, somebody is a doctor is putting WhatsApp. Could you able to ask questions directly to our speakers if you are an online?
Sir, you are asking some questions, no, sir? Ishwar
Yes,
Murthy,
yes,
sir?
yes. Actually, I have only one question that is connected to what you call that. And you mentioned in your first initial slide, there were what you call that, and the green hydrogens, the minimum carbon dioxide CO2, which is a minimum 0.9 to some 1.2 something.
Per kg of hydrogen
Yeah,
production.
yeah. So that is connected to the which that the material fabrication of that green electricity component or
Yes, yes, sir. Why?
okay.
Because whatever the green electrical energy you are using,
Ah,
50
that,
units is required per kg of hydrogen. Rough amount, I am telling.
yeah, yeah, yeah. That is
For that
correct.
50 units, at least 40 to 60 grams per kilowatt hour energy, CO2 will produce manufacturing of the renewable component.
Ah, understood, understood. Okay, okay. Thank you, Reddy.
Yes.
Thank you, thank you. Now I got it. So,
Yes. Why? Because some of the researchers is there means they can't use the zero like
they
where
should not put zero. So practically speaking, what you call the making component cost and its production of CO2 emission that
yes,
we are
yes.
supposed to consider into that account. Good.
So based on technology, that value may change.
Yeah, correct.
Yes.
Thank you. Dr. Trijo, so you are asking some questions. Yeah, please.
Yeah. Hello, sir. Can you mention the startup opportunities available with green hydrogen?
Could you introduce yourself? Where are you from? Switch on your camera. That will be visible to other participants also. It's
I'm sorry, sir. My camera is not
oh
working.
no issues. No issues.
What do you want, sir?
I'm from Sri Buddha College of Engineering, Kerala.
Acha,
Okay,
acha.
sir.
Okay, good.
Okay, sir.
Sir, can you mention the startup opportunities available with green hydrogen?
Sir, your voice is not clear. Hello?
No, he is asking the startup opportunities in the green hydrogen domain.
Yes, sir. That electrolyzer manufacturing or rest of the components also. Rest of the plant also. The integration of the system. That is also one of the important component.
Exactly.
Especially for mechanical background persons. At least I think new proposal, I think they are inviting the proposals. Rest of the plant, whatever the components are there, their manufacturing also inside, especially compressors. 700 bar pressure, we want to compress the hydrogen. for the filling station purpose.
Okay, thank you, sir. Thank you, Dr. SivaReddy. So, if no questions, then we can close this the fifth day first sessions. It is my honor and privilege. I sincerely thank Dr. SivaReddy for spending your valuable time and sharing various policy matter on this green hydrogen economics. Probably it will reach to almost 160 participants with us today online, and almost all the people will take in some message. It will be useful for them, so they might be start their own startup, or they may start their own what you call it and the research on this green hydrogen project work. So once again, it is my sincere thanks for your valuable time with us. Thank you, sir. Thank you so much, Dr. SivaReddy.
Thank you, sir. Thank you for calling me also.
No,
Thank you very much, sir.
no, it is my pleasure. We have almost 15 years, 15 more than 20 years relationship. We are
Yes,
maintaining it as a brother, as
yes,
advisor. So it's
yes.
good. So it is very happy to be here with us on our FTP. Really, this is good information.
Okay, sir.
Thank you, Reddy. Thank you.
Thank you.
Now over to the next session. I invite my coordinator, Dr. Rajiv Kumar, to introduce
Thank you,
the.
sir.
Yeah.
For the next session, we have our speaker, Dr. M. Eswaramoorthy, sir. I will briefly introduce, sir. Dr. M. Eswaramoorthy is serving as Professor of Mechanical Engineering at Sri Mata Vaishno Devi University, Katra, J&K, since August 2018. Previously served 20 years at different technical institutes which are affiliated to VTU Belagavi, Anna University, and Kannur University. He served as the Registrar, Dean Faculty of Engineering, member of Governing Council and Academic Council of Sri Mata Vaishno Devi University. He has awarded as INSA Visiting Scientist in 2021. He has obtained Bachelor of Engineering degree from Kongu Engineering College, Perundurai, then affiliated to Bharatari University, Coimbatore in Mechanical Engineering, and MTech in Energy Technology from Pondicherry Engineering College, now Pondicherry Technological University, affiliated to Pondicherry University, and PhD in Mechanical Engineering from NIT Tiruchirappalli. He had short academic visits to International Center for Theoretical Physics, Trieste, Italy, and National Institute of Fundamental of Study, Kandy, Sri Lanka. He is a recipient of Best Researcher in the Area of Renewable Energy of the 2021 award by Indian Society for Technical Education, New Delhi, and Young Scientist by Vision Group on Science and Technology, Government of Karnataka. He has served as a reviewer for DST SIR project proposals and reviewer for Elsewhere, ASME, and Springer publications, reviewed about 100 journal papers, and organized 10 DST SIR AICTE sponsored workshops, FDPs, and having more than 33 SCI, SCIE journal papers and 5 Indian patents in Indian Patent Journal at his credit. So we welcome Professor M. Eswaramoorthy. Over to you, sir.
Thank you, Dr. Rajiv. It's my honor to be with us at the role as a speaker of this session 10 of the day 5, the last session. Thank you, Dr. Rajiv, for giving me a brief introduction about me. So it's as per the timetable, I supposed to talk about this solar thermoelectric hydrogen generations. So I like to take into that my slide. So where where we are living. So now currently we are in Udhampur. So we're in Ladakh, Jammu and Kashmir Union Territory, a new map, political map of India, in which we are here in Udhampur. We're in SMVDU, where you might be seeing the sponsoring agencies and other participants as per your map where you are from. We are accessing today because of this internet technology, because of the help of an AICTE adult support. So this is my institute where I working currently. So where it's an entrance of this university gate. So where that the below this line where this you can found that mountain in which it was taken the sometimes back. It is during the winter seasons where in the yellow color it's a snow which is falling for it was still was there. Probably that the backside that there will be what you call the Mother Vaishnu Devi, which is Mother Vaishnu Devi cave is there. The people used to pilgrimage, used to visit for the darshan even in 365 days. It is only the famous because of that Mother our institute is existing and we are here. There, I think in 2017, Prime Minister Modi is delivered the cheapest
Your
address.
slides are not visible.
Sir?
Sir, please maximize the
Slides
slide.
not visible.
No, I am. Voice is not audible.
Full, sir, slide do full screen.
Acha, full screen, okay. Yeah, it's full screen only now. It is not there.
No,
Not
sir.
yet? Okay.
No, sir.
Okay, sorry. I am facing some problems here. Now is it visible full? No.
Yes, sir, you can continue.
Thank you. Now what do you call that? I like to continue here. So this is in where the Matri auditorium in which the middle portion where this bottom the convocation was happened here, where my institute that auditorium friend we are in a part of what you call it in 1 megawatt solar PV power plant. It's part of our clean and affordable energy sustainable development goal. So. Before that, so I like to give the highlights where the even in previous all 9 speakers are discussed various green hydrogen companies. I like to also highlight when in the form of that logos where Adani's, Reliance, Indian Oil and Natural Gas, then Gales, Bharat Petroleum, NTPC, L&T. JSW and ACME, these are the people, they started the business in this green hydrogen generation. When they found out as per the green hydrogen mission, there was huge potential. Then this company which needs some human resources, which required some amount of what you call the fundamentals knowledge on green hydrogen things. So my talk will like to give some background what thermoelectric generator, what is in hybrid energy systems, what is the solar hydrogen generation systems, where the combined energy system and research area and future work on this green hydrogen as well as solar to hydrogen output and conclusion, and with some acknowledgements here. So where the background, so India is going to become what you call it an energy independent by 2047. 1947 we got an independence, but after 100 years, so the government is decided what you call that and be an energy independent. That means we are still dependent on what you call that an energy from other countries. Almost 40% of our primary energy sources we are taken from other countries with the 19 90 million US dollar. That's what an import bill which is going to be says. Where again it was saying that the report which say that again it's going to rise almost to 6.5 worsened in the September. It was an earlier report. So that is a what do you call it? Trends where this in India has given deep commitment on this climate goals, where is universal goal, well, in which we are in the fastest growing on the renewable energy capacity in the world, as per the our government of India Ministry of New and Renewable Energy report is concerned. Also, we are what you call it, India's most attractive destinations for investing in the renewable energies. That many foreign companies which is coming in India, where this energy independent by 2047. So we are having a site. Also.
Murthy sir, I think slides are not changing.
Okay.
We are saying that top 10 green hydrogen companies.
Still okay.
Now changed.
Now it changed, huh?
Yes, sir.
Okay, I think the full menu it's not coming up. So can I manage with this one? So
Excuse me, sir.
yeah, please participants, please you can share.
Uh, for that, you are sharing entire screen. Actually, you are sharing only your slide, only you are sharing. That's why you are going to presentation
Okay.
note that time, not share.
Okay.
Okay, thank you, sir.
So now that my screen is here, and the background where we like to have what you call it, 2047, we are going to be energy independent and also want to achieve net zero emission. Net zero emission, it's by what you call it, 2070, as per the COP 26 commitment by our government of India. Where the COP 29 is coming up, where this slide, where the right hand side national green hydrogen missions already discussed with all the speakers, so don't want to discuss further, where India crude oil is going to import again what you call it in 6.5% in September 2024, where we are committed on this climate goals, where what you call it, and we are India is fastest growing in the renewable energy capacity in the world. So as also one of the emergent destinations, where the attractive destination for investment in the renewable energy, because that India map, when we consider almost 756 gigawatts of solar energy potential is available on the land surfaces, where our in total installed capacity as on today, so 450, where we are sufficient in availability of solar radiation. If we convert those into that useful energy, probably it's we can achieve net zero by 2070 easily. Then energy use has doubled in last 20 years. So before the Congress government, or what do you mean to say now, it is so 2019, sorry, 1990, almost from 2002 here now, so the energy use has doubled, and also at least another 25% by 2030. So that means currently we have in 400, say the 25%, it's in 500 gigawatts is going to be added in 2030. Then the critical role of green hydrogens with its vast renewable energy resources have the opportunities to produce the green hydrogen for the world. So based on this, it is that National Green Hydrogen Mission is established with an aim to provide a comprehensive action plan establishing green hydrogen ecosystem and catalyzing the systemic response to the opportunities and challenges in this sunrise sector. Then India growth story unfold. Its demand for energy and resources is set to rise. India is currently import 40% of the primary energy requirements over the US dollar of 90 billion every year. So this was data. It is 2023 when Green Hydrogen Mission was established. Now that 2024 in September, it was saying that it's 6.5% is again improved on the energy import will. So probably it may be in 100 billions US dollar. So mobility and industrial production sector are mainly dependent on the imported fuels, the petrol and diesels. That's what they're talking in this meaning. So the necessary shift towards technologies which enable enhanced share of renewable sources. The energy mix we can mix with what you call the fossil fuel to reduce its consumption rate and and also reduce its reliance on this fossil fuel with an aim of an emission also it's coming into the pictures. Now these slides I like to have some of what do you call that solar. First I will start with some of what do you call that solar photovoltaic
sir?
or in independent. Yes.
Sir, can you please go to slideshow, sir, because the screen is very small, which means it is not in presentation mode.
No, I understand, but when I go for the presentation mode, so it is not visible. So there was some technical glitch. So could you bear with me?
Okay, sir. Can you please go to the tools, sir? Top side slideshow is there. Can you please click that?
Which one? Which one?
Top one, top tools, home, insert, draw, design, transition in that slideshow. Sixth one. Home, insert, draw, design, transition, animation. Then next is slideshow.
Home, insert, transition, animation,
Okay,
slideshow. Yes.
that from
Okay.
current slide. Second one. From current
Second.
slide.
Is it visible now?
No, sir, it's not changing. I think some problem is there then.
Yeah, so I am using some old system. That's probably there is a problem here.
Okay.
Sir,
Fine.
when you're sharing, you can share entire screen, sir. At that time, we can see. You have shared only the windows now. That is the reason it's not showing.
Okay, thanks for your input, sir. So let me also try with your technical support. If I go stop, so I will once again I'm sharing with your input. I want to share that entire screen or window.
Entire window, sir. Entire window.
Entire
Yes,
screen,
yes,
sir.
yes, yes.
Entire screen.
Yeah. Now, probably it will be visible now. And then what do you call that? Slideshow from the current slide. No. Is it okay? Is it visible, sir?
Yes, sir. Visible. Okay, sir. Fine.
Thank you, dear my participants, for your technical input on this. Yeah, thank you. So now, I like to carry my what do you call it in the presentation. I said in various different kind of electrolysis which is available for the hydrogen generation, but the input that's supposed to be in a green electricity, the green electricity is supposed to be taken from this solar thermal route or solar photovoltaic route. The solar thermal and photovoltaic route, which is also having the low efficiency, but if you enhance it in efficiency using thermoelectric, using PCM material, it will help to what you call the increase the overall energy conversion efficiency. It helps what you call the reduce the total cost of energy, green hydrogen production. So now I like to give it in what you call it in some different that available literature state of art technologies, which is available in and the literatures. So where the solar photovoltaic photovoltaic thermal PVT system, only the thing is it is going to be increase its efficiency. Many researchers working in solar thermal, you might be understanding it. So where this collector, which is in thin film technology or amorphous technologies, what do you call it in solar cell market, where it's going to be used some the coolant materials, different air cooler, what do you call it, an air collector or water collector, or combination of nano fluid, these kind of things, which is helping to enhance its thermal efficiency. That's what it's an overview in which what do you call it, and they mentioned the system is going to generate both what do you call it in electricity as well as a current simultaneously. That is an additional advantages in the systems. Now, so I like to give what you call it and some other work which is in a reported very recent, just four years back. The people working on this what you call it and calcium arsenide PV cell, so in which they're adding expanded graphite in paraffin. So this 2019, even in 2014 also, 14 and 15 also, people are used this in expanded graphite within PV, and I will show you in the current slide. Probably you can understand how these things are happening. The people are getting in SCA journal publications. So where this picture, which is in your right hand side, it shows what you call it an expanded graphite is nothing but in the form of powder or in the form of grinds. That's what in expanded. Then paraffin works, with mixed with what you call it an expanded graphite. It shows the color what you call it in black. That's what A and B pictures, where it's in copper form and paraffin copper form mixtures. That also they are adding what you call it in this as a PCM plate, wherein PV cell. There what do you call it thermoelectric model. So my arrow is my mark. Sorry, what do you call it? My cursor is showing in your slide. It's visible.
Yes, sir.
Yeah.
Yes, sir, visible.
So what this point, which is called what a thermoelectric model, where this bottom side it's called it's in cooling devices and top side it's hot surfaces, where where this black color it shows what you call it calcium arsenide PV cell, where the concentrated solar radiation which is falling on this concentrator, and where the concentrated PV cell which is going to be converted electricity, where the amount of heat which is going to be melted, the excess heat from this photovoltaic cell which is going to be acted as a hard side of the thermoelectric generator. So now the PCM plate which is acting here as hard surfaces, people worked on this. It's also getting published in 2019. Some people they worked with cooling devices. So I will show you in the next current slide. Probably it is a solid paraffin, where it's a PCM plate, where it's heated. Once it's heated, it's going to be heat energy is going to be gained from here. This solid paraffin is converted into liquid paraffin. So that's what it's liquid paraffin, this side which is going to be mentioned. So this acting as what you call it heat sources to the thermoelectric generator. How this thermoelectric generator looks like, I will show you in the next slide. So this solar still, which is using phase change material and nanoparticles, I like to skip it over here. It's not relevant to us. Where this solar air heater integrated with helical tubes carrying phase change material is only the thing is heat storage, which is using in paraffin wax, which is helps to enhance its the performance. So they are used in different applications. So let another, it's an air heater. Let me skip it over here. That air heater with micro encapsulated PCM capsule. So I think this work, it is a very old one. It's done in what do you call it, NIT Calicut, Professor Jairaj and team. Then the pin solar air heater by using latent thermal energy storage. So where Daily efficiency. There was a mistake. It's here. Daily thermal energy conversion efficiency is an appropriate word. So with PCM, probably you can notice down it gives what you call that better efficiency than without PCM. So then another thermoelectric rooftop solar collector power plant. We are in the winter. We feel it's what you call a room supposed to be cooled, but it is in summer after 4 to 5 months. In the summer we are in more humidity. We cannot live in what you call it in this inside our house. This work which is reported here, it was done at Thailand. Thailand in the summer it's very humid and very warm. So they are using these thermoelectric technologies to run what you call it and the proper cooling circulation and things. The work which is going to be used here to generate additional what you call it electricity to run the flow. That's what. So the people in this research work, people are working on the thermoelectric generator. So for power generation mode to run small application where run your flow or what you call it charging your battery. So these kind of things which is happening in this study. So where again it's a 2019, I'm coming into the pictures where what you call it and the photovoltaic and PCM models, and it's an energy flow where the PCM which is going to be used here, the phase change material which is used here to remove this excess heat from the PV cell. When the PV cell temperature is going to be rise, it's going to lose its electrical generation performance. So we have to maintain its in optimum temperature. That is maybe based upon the materials. based upon the PV cell material, that operating temperatures, optimum temperature is going to be vary. That we have to maintain based upon that operating temperatures. We have to use the PCM is having different melting temperatures. That particular melting temperature PCM we are supposed to use it here. So probably it will be helping to maintain that PV cell at constant temperature and for the maximum power generation point here. So this is overall picture where in which what you call it and how the structure of this component which is going to be happen here, where the class which is in then it's connected with some gap and PV cells. Then Teflon coating, it was say TPT, where the contact layer, where in which the PCM is going to be fixed over here. Then the photovoltaic panel again is integrated with the PCM material. Then the other papers which is also reported, where in which we can say they're using in this concept the personal lens. So they done some experiment where the PV cell which is going to be placed over here, it is also concentrated PV cell. It's going to be generate so some amount of electricity. Then there's excess heat in the PCM which is going to be used for generating electricity from this thermoelectric model. The total concept here, they are adding one additional component, PCM and thermoelectric model, and heat sink, it is an air-cooled heat sink. The research work, the people are working on this PCM and the heat sink, the different heat sink and different thermoelectric models. Thermoelectric model also a lot of what you call the research work which is happening. That also I will share. So where it is in a single junctions and thermoelectric model, where combination of total system, how that efficiency is going to be improved. From your left hand side, it shows very clearly the combination of system where in a red the star mark which is having the highest efficiency. Even in the efficiency of any thermal system, if improves 0.1% or 0.1%, it's a great achievement. It means without any additional what you call it an extra heat input. So we are taking in power output. It's 0.1% is an improvement. It is an improvement. So another thing is the people can work on this solar receivers, where solar particle receiver, it is also used in solar thermal power plant, where in order to increase the overall efficiency of the power plant. So it works on what you call it in solid particles, which is works on extremely high temperature above 1000 degrees centigrade, and received considerable attention from the researcher in the field of concentrated solar power during the past decades. So where this supercritical CO2 power plant, so which is working, giving an attention on the Bredan cycle to enhance solar to electricity efficiency compared to organic solar Rankine cycle systems. Organic solar Rankine cycle efficiency system, it's very low. So compared to SCO2 Bredan power cycles, the thermal performance, so which also going to be depends upon the receiver system design and the particle flow characteristics and the properties of solid particulate matters. The solid particle receivers, so it is a different kind of mechanical arrangements. So it was reported very recently where downflow, offlow, the horizontal flow. So and based upon what you call the fluidized particle flow through codes, fluidized bed receiver, and inclined plate counterflow, then triangular shaped mesh stretches, different mechanical geometries, then supercritical carbon dioxide SCO2 Bredan cycles. So it was in the power generation technologies. So used in the supercritical CO2 as a thermal transport fluid. So where this supercritical CO2 act as a transport fluid. So again, no need to discuss. It is a thermodynamic process. It is a Bredan cycles. So let me go for the challenges. It is a material problems due to high temperature and high pressure, and also it's a limited efficiency to that the metallic materials, the structure, small specific work compared to the organic cycles, large systems volume. And future research on this topic, it is focused to improve the turbo machinery efficiencies, design combat heat exchangers, and building large-scale experimental facilities, and optimizing configuration and improving the control strategies. These are some areas where in which supercritical CO2 Predan cycle is going to be improved. So this CS supercritical, what you call the 10 that components, it is reported it is a German aerospace. Whenever we go, so we are technically we are following with the Germans. Then the technology, whatever technology we received, the solid particle receiver, which is mentioning over this component on this solar tower concept, where it's in a helioside field where the received reflected radiation which is striking on this observer plate receiver, where the hot particle storage which is going to be stored, and where the particle supercritical CO2 heat exchanger, it's going to be exchanged at a high temperature and high pressures, where it's a whole, once the heat is going to be exchanged in this cold particle storage which is downward, again it's moved, this cycle is repeating its heat collection unit, where other the compression SO2 recompression Predan cycle which is working on this Predan cycle power plant, where the generator is going to generate this system efficiency. It's better for existing solar systems, where this CSP plant with the closed loop but SCO2 Predan power cycle, which also so reported here. So in which this technologies which is happening here, they are using SCO2 Predan. Here this heat storage unit and turbine, recompressor, so and the main compressor which is unit, other heat exchanger and the recuperator type, and high temperature and low temperatures which is used to collect, recycle, what you call it, and recycle and heat exchange. So probably it also give what you call it, and better efficiencies. Then CSP integrated SCO2 oxygen combustion cycle, which is also the reported very 2019, where in which the cycle which is happening here, that CSP plant, where it is concentrated solar power plant, where in which other conversion unit, the turbine compressor generator, it is in compact in nature here, where the CO2 storage and supercritical carbon dioxide system which is happening over in this, where the heat sink can be stored. Another future technical target on this component of next generation receiver. So only the thing is, ultimate aim, whatever we are discussing on supercritical, high temperature, low temperature systems, once these are the route where the renewable energy which is coming up, this energy can be used for the electrolysis. That's what we are focusing on this in area, where in operation and maintenance target. So where it is this based upon what you call it in years work, it is in 2020 that cost, all the cost which is mentioning in the dollar. So where the Indian such a report which we could not able to found out, but it is a target and a technical target in the futures, where the thermal storage, where the efficiency, where it is 99%, it's an exergy efficiency also it's 95%. Cost is come down, it's an energy is in $15 per kilowatt hour. Power cycle inlet temperature, it's greater than 720, where it's in power black efficiency. Net cycle, it's a very great 50%, it's a very good efficiency power black, where in a simple Rankine cycle or integrated Rankine cycle, it's also reaching almost 50%, but the system is completely on carbon free energy system. That's what we are targeting on this. The heat transfer medium, where the thermal stability can also what you call it in greater than 800 degrees centigrade, compatible with recommendation performance, compatible with thermo electric storage performance, where the levelized cost of electricity, it's a target $0.05 per kilowatt hour. So it is a target where this 6.2 megawatt national solar thermal test facilities is Sandia National Laboratories, where it is in Foxside. Probably we might be seeing the Foxside. It's minerals, rock minerals. It is a sedimentary rocks. That's all the main sources of aluminum and selenium in the Foxside. So where there's a variety of minerals which is include the subsite, then that colonite and ilmenite, so where in which the foxite they are taking it that whatever the person which is carrying in hand, it's a foxite material which is used for the solar thermal test facilities at in Sandia National Laboratory in US, where this component which is happening here, it is in a overall structure where in a pictorial view, where in a schematic diagram it shows the component, various component. Starts with an heliostat where the particle heat exchanger we seen in earlier in schematic diagram, where other conversion route, energy conversion route with the heat rejections, where in power turbines, where it's in generator and electric grid. So the thermal energy receiver and thermal energy storage system which is happening over in this pictures, where the hydrogen can be processed. So where SMR techniques, what it's called, it's a steam methane reforming process, and it's in applications where it is taken as in the heat sources. The heat source, a concentrated solar power plant supplies the heat needed for its steam methane reforming. It is in competitive cost. It's a solar reforming can have the competitive cost compared to traditional fossil fuel systems. It is sustainable, and solar reforming more sustainable approach to conventional steam reforming. Then it's a green hydrogen produced solar reforming of renewable feedstock is 100% green, where it is an T-sulfuric station. What is a methane? But it's raw material which is CH4, the pre-treatment process, where it's used in a reforming process using concentrated solar energy, where it is in the reactor which is performing and SIP reactor, where we are adding with the steam that is in form of H2O. So when it is a purification and process of reform made case, which is happening where removal of this H2O removal, then the remaining CO2 also it's removed from here. Then we taken in the hydrogens. Hydrogen can be used for in various applications for electricity generation, transportation, and chemical and residential and industrial. So this steam reforming, so this the feedstock as far as 100% is renewable here. The main characteristics of fast and forcing future generation of compound solar parabolic plants, where the generation is started with what you call the first generation, second generation, and third generation. So we are in the running of the third generation. It's an expected what you call the Ruby and greater than 700 degrees centigrade. The receiver outlet temperatures. First is when initially it was started with an parabolic trough, then linear Fresnel reflectors, then this temperature almost 250 to 450 degrees centigrade, and second generation up to 565. Then parabolic disc concentrator, it is that's what it's taken in PDC, it's 720. But so where when we are using what you call the salt particle size gas, this heat transport medium, so we are they are expected to be in greater than 700 degrees centigrade. So it is a very quick review, so quick impact, so in which we can easily note that the annual solar electric efficiency, it is in 25 to 30%. There, what you call it, and design cycle efficiency, it is in greater than 50%. Then peak temperature in a cycle, it is 700 degrees centigrade, where the power cycle, it's a Pradan cycle. So if you somebody want to work on this, what you call it, the solar steam power cycle, so better you can work on this Pradan cycle, take relevant literatures, then probably you will get some idea where we can start. So it will be a good market. Probably the funding agencies will give for what you call it in simulation work, as well as in a small experimental or startups also even too. So concentrated solar power development path from 1982 to 2030. So it start with the solar 110 megawatt. So where it is in 2030, the supercritical CSP plants. That's what its various stages. The technology is grown. But we like to always focus on a forward. Forward is a 2030. It was mentioned here. So supercritical CSP plant, then higher working temperatures and new storage concept, hybridation of the with hydrogen and biomass. So probably it's take more relevant literature. Probably you can work on this in concept. So you will also be in what you call it in a researcher or as well as a startup Indians. Now I like to give what you call it in some of other technologies which is in power generations using in a novel concept of hybrid solar chimney power plant. Probably the faculty which you are teaching in the mechanical and renewable energy courses, probably this concept might be in a part of your syllabus. But this work which is in reported almost 2021 on the sustainability, they are using some technologies where they developed one. This one, what you call it in system, it's a 200-meter height solar chimney is developed, where the hot air which is going to be shucked over here, put into the natural trap where the turbine is going to be placed. It's going to be create a natural trap where the turbine is going to be operate because of this natural trap system. It's also going to generate some amount of electricity. So only the thing is this setup, it's made with what you call it in one small setup. It's a chimney where in a compensated this it is in the sea waterfall in which they're made it in a collector, where this collector is going to convert this water into steam. That's what is the steam water collection which is going to be carrying this compensated water. Now it's air movement which is going to help this what you call it turbine is moving. When using operating as a solar chimney, when if you operate as a cooling tower, so probably it also work in this turbine also working. So we are also going to be generate some amount of electricity in the things. It is a simple concept, both in a charging mode. That's what it's in and cooling mode. We are generating electricity. So it is a good concept. Where the generation of green hydrogens. So it is simple techniques. So simple diagram here. It is a power source. That's what it's. So we are power source if we taken from the renewable energy based power source. So completely it's a green, where it's we are running with an electrolyzer. Why the people are using in electricity and electrolyzer? Electrolysis already technology driven TRL rating. It's in known technologies. It is in more efficient systems. Even in alkaline at low temperature, people are working on that. It is having in the highest efficiency. The thing is the catalyst which is used in alkaline. So that if you found out any alternate materials, alternate catalyst or membrane, it will be best one better systems. Where the generation of green hydrogen, this slide which is happening, which is showing what you call it, and that electrolysis component, where you supply with an AC and not an alternate current, it is a direct current. So we are adding one input, direct current electricity, and water is an input, but we are getting in a product, it is in H2 and O2, and some amount of heat which is coming out of the system. So we are taken in two input. So it is a chemical systems. There is no combustion here. So only in the chemical reactions in which it's need electricity, direct current, as well as the water. It's going to generate O2 separate and H2 separate and different cathode and anode and ionic exchange or whatever the chemical reaction which is happening, and heat is part of the heat. Where another devices which is very interesting one, what you call it, and the photoelectrochemical device for solar hydrogen. But whatever it is not technology proven, it is a lab scale model. It's not much more in efficiency, but we like to skip it over here. Then chemical looping of hydrogen production and power generation system driven by solar energy, where the steam methane reactor, so that's what, so steam reactor, where the fuel reactor, and this methane, I think CH4 is here, where it's turbine which is going to be working, so where this hydrogen is produced in this steam reactor component. Another, the solar hydrogen generation system integrating photovoltaic cell or photon enhanced thermionic emissions, where this system which is produced are many advantages. It is a carbon-free, a renewable, versatile, efficiency, and affordable and environment-friendly energy storage in the independent and stability. So probably you can easily have a look on this. The water, again, it's an inlet here where it's an photon enhanced thermionic emissions. That's what PTE. It's working on ionic exchange. Where this graphical presentation, it's an application side. So we like to skip next one. This also it is on the hydrogen generations with in detailed isometric view of pictures. Then some system which is going to be recently published, it's in 2024. It's where then combined the cooling, heating, hydrogens, the power. This any system are having a multiple uh, futures or multiple output, so it will be attracted. The system which is developed here, it's going to give the cooling effect, it's going to give the heating effect, it's going to be hydrogen generation, and also it's a powering up. It is a multi-generation system. Very simple one. Those are interested, you can also have a look on this, where that's a PV cell which is going to be fixed over here, where it's mentioned where this tracking, where the optical and the PV sub tracking systems, where the solar collector, where the solar PV output always is electricity, where the solar collector, it is a thermal collector. That's what it's heating which is happening over here, where refrigeration cycle and the cooling system which is happening on this refrigeration unit, where the reactor, what do you call that, and gas mixtures, whatever the reactor which is in there, hydrogen is going to be generated. So this entire system which is happening here, it's a multi-generation unit, where the hybrid system based on solid oxide electrolysis, then and solar energy and molten carbonate fuel cell, where this journal of energy. So it is also recent paper where the working on the solar disk collector, which is going to be used for what you call it, and solar PV systems, where the thermal receiver. So in which, sorry, in this thermal receiver, amount of heat which is going to be used here in a heater, where which is going to be used for this PV collector output, which is used for solid oxide electrolysis. Then whatever the energy, the hydrogen which is produced, used in hydrogen storage, then again it's used for what you call it, and fuel cell component. In the way which is used, they're looping, integrating the things in a output, probably for a different output here. So again, it's another, the solar hydrogen generation with direct coupling, photo and thermal energy. It is also what you call it, performance improvement. It comes around what you call it, and 32.33%. It's an improved on the performance production, and also reaction temperature. It's going to be more than that 10 degree. It was in recent papers where they're used many catalyst, the copper, zinc oxide, aluminum oxide. So where this systems very simple in nature, they're working on this. Then again, another solar chemical water splitting with an cerium oxide as red oxide material. So how it's going to be work on this one? Step one, red oxide material is heated up with an to 1400 degrees centigrade to release oxygen and the reduction. Then oxygen with water molecules oxidize the redox materials, thus the producing hydrogen. It is symbol one, what you call that, in structure and method. We can also work on this. Then overall layout of the receiver, reactor, and solar thermochemical hydrogen generations. So this also very recent papers where we can concentrate this what you call it in solar energy on the concentrator. So in which different what you call it in our 400 it's in the fuels which is flowing. So various chemical processing steam. So process in which the hydrogen is going to be generated in this systems. Where the cycle efficiency, it's water splitting almost to 15 to 30%. That has challenges on the material problems and also re-radiation from the reactors and lower absorption efficiencies. Then some work which is connected to what you call it geothermal renewable energy sources, renewable CCHP system, which integrated with the battery banks and hydrogen energy storage. It is working on this the combined system principle where they are working on this PV thermal. So again, it's pump back and the electrolysis they are using it here. That's hydrogen is going to be stored. Then again, which is used for the fuel cell, which is run then electricity, the heat pump, and the cooling coil for this unit. So it is a part of work we can invested on this topic. Then mid and low temperature solar hydrogen systems, which is happening. Which is also have the different so promising method for generating hydrogen using solar thermal energy. It has several advantages include so efficient energy storage. The chemical energy produced can be stored for later usage. Then hydrogen in the form of chemical is used for in a later storage. Then reduced CO2 emission. The process is driven by solar energy. There is no need for the fossil fuel CO2 emission. The high purity of the hydrogen is produced that can be used directly in a fuel cell for generating electricity. Where the hybrid biomass power systems that also they're generated what do you call it electricity here. They're used different when you're looking at this the electrolysis, they might be used the FEM electrolysis or alkaline electrolysis, where when you're using for what you call it low temperature applications, where in a photovoltaic or in a solar thermal system, if the concentrated solar PV is coming into the picture, concentrated the thermal system is coming into the picture, they are using solid oxide. That until it's a high temperature applications, please you can keep it in the mind. Where this hybrid biomass solar power system, where the benefit it's known to fact, it's provide it's a reliable power without any what do you call it and weather and time. So and also cost effective and helping electrify in the rural areas, then create jobs. So it is a common dialect, so probably we can easily understand. Then general process of methanol synthesis from captured CO2 and renewable hydrogens. So there it is an overview. So it was given it's a power plant, cement plant, and chemical plant, where this carbon CO2 which is emitted, they're using in some capture technologies. Then CO2 is going to be taken here. Where this solar, wind, geothermal, hydraulic that we're using a power generation technology, they're using electrolysis method. Hydrogen is going to be generated, where it's going to be used for what you call it an methanol synthesis process. It can be used distillation and methanol, or it used for the power generation. So it is used for the power generation method. Again, it's integrated solar driven hydrogen generation by pyrolysis and electrolysis coupled with the carbon capture and Rankine cycle. So probably if you found out here where the Rankine cycles, where the steam cycle which is coming into the pictures, the steam which is recovered from this heat, it can be used for steam cycles, where the solar furnace which is going to be used in heat exchanges, where this syngas or pyrolysis method. Again, what you call it, and it is acting as a catalyst where the hydrogen which is coming out in the way, then electrolysis which is used for what you call it, and hydrogen generations. Again, this method, the heating, cooling, and process. The multi-generation system with an integrated solar energy combining energy storage, the cooling, heating, and hydrogen productions. So it is in a different study no, published very recently. It consists of that heat exchangers where it's heat exchanger where in which it is going to be used in a solar concentrated solar heat, where this FEM electrolysis and the storage of hydrogen which is going to be used in this component, where when electrolysis, where O2 which is coming out, they are separating the O2 and storing it where in required, where what you call it, the FM electrolysis which is also powered by another solar PV and thermal PV panel. So solar PV and thermoelectric also we can incorporate it here. So it is also generates some amount of electricity that is used for what you call it, FEM electrolysis. Where at other the thermal power plant which is used in this systems, it is used for the cooling cycles where the condenser is coming to the pictures, where again the component they are adding it here, the wind energy. So wind energy where this the mechanical power where they're taken into the compressor, that can be used in the condenser component. So that again what you call it, and it's a heat storage, then the combination of other it's cooling cycles here. So there are multi-generation system which is mentioned over here. So another component, overall water splitting in the reaction basic principle, where it is number one, the water splitting, then again photocatalytic and heterojunctions, electron cool fair separations in which the hydrogen is going to be generated as the physics point of view, the chemical point of view. Then photocatalytic water splitting in the mechanism on the semiconductors. So where it is the process use the light energy water and the catalyst to produce hydrogen and oxygens. So promising on the sustainable and environmental friendly way to generate hydrogen fuel. Solar to hydrogen efficiency of catalytic water splitting is very low, so the research is achieved only the 9.2%. Only for the research work and academic, so academic research, the people are working on the materialistic and the commercial, still it's not achieved, where the commercial leader is in electrolysis, they're more than 60% efficiency they're achieved. So it's only on a research point of view, so where this photocatalytic water splitting mechanism. Then cadmium sulfide, it's another rare minerals, the green and halite, the more common and impurity in zinc ores. The main sources of cadmium for the commercial applications because of it easy to isolate and purify. The pigment used, the main paints, plastic, textile, and ceramics. So some of the things, let me skip it over here. So the hydrothermal synthesis of cadmium sulfide, how the cadmium sulfide is synthesis. So the techniques which is in a hydrothermal where it is a morphologist, it is seen it's something like in a flower. Solar motion based, so another technologies which is which is integrated with new hydrogen generation systems, where they are using ocean wave energy systems, which is also used for electrolysis. Probably these things which is happening for an electrolysis method. And there another, it's a solar based system, solar based power system. It's going to be generate using a steam Rankine cycles, and another one is an organic Rankine cycle, and also it's another the multi effect desalination, that is called MET, which is used for water purifications where you might be seen where in which what you call it in the fresh water tank which is going to be taken for used for what you call it hydrogen hydrogen generation through electrolysis. So this system, so it is a, what you call it in a simulation or what you call analysis point of things. It is also having an good point of things further study or further research. We can make it consist of many components. That's what I was thinking. I'm sharing with you. So where the useful output probably you can say it is an electricity, the fresh water and hydrogen three output which is coming. That's what it's multi generations. Now I come to the small work which is already published. It may get some insight for your further studies. Where this thermoelectric generator I was mentioned, it is what you call it, taking in input solar radiations, where in the hot side, where in the PCM in the cold side, it is taken where the PCM it's low temperature, it's where the radiation is high temperature. When its radiation is not available in the night time, probably it is an item, it's a convection which is happening. The PCM stored energy which is going to be act as a hot side. So this system which is going to be operate 24 into 7. They made small lab scale model, so it's going to be generated what you call it an electricity to produce to power some small mobile charge or what you call small LED lamp. So that also it's a basic work where they mentioned that what you call it an minimum temperature which was happening over that with PCM. Now the thermoelectric generator, whatever I said, it was worked on various combinations: solar thermoelectric, biomass thermoelectric, geothermal thermoelectric, and waste heat thermoelectric. It is used for what you call it an electricity generation and water heating system and freshwater production and hybrid system. It's various application it is used. So it is a main edge and it can be used for many applications. So again, I like to skip, already we discussed. Then this thermoelectric generators where I told there are some couple of work which is also happening where you might be seen it's an thermoelectric generator efficiency is improvement on based upon the leg geometry. Leg it is in a square, so where in the one leg it's square, another one is a trapezoidal. Where it's a leg, it's going to be changed over here. Then both the things, what you call that, and it's a conical in shape. There is one conical shape, one two what you call convergent and divergent section. Both the things is a divergent section. There are many geometry of thermoelectric legs. It also gives what you call that a very large scope for enhancing it research potential. Even in thermoelectric models, that's a power generation model we are talking. Where is it works on the Seebeck effect. Another one is in the Peltier effect. It is a cooling model. So we are not talking about that cooling model, but it's a reverse phenomena of that Peltier. It is a Seebeck. But here some of the report which is recently published, which where it is in the hot flue gas which is flowing on this your two-wheeler exhaust. They are keeping at the outer cell using this what you call it and hot and cold, and where this N material on this cylindrical in shape. So where it is a flat in shape, where this section is good cylindrical in shape. So I like to have some idea, some what you call it in work which is published. Show to you. So it is a solar PV panel in the backside. It's a backside. It's called as a Teflon. Where the Teflon, it's a, what you call that a layer material. So where in which there are 1, 2, 5, 6 thermoelectric model is fixed. The thermoelectric model hot side is fixed on with Teflon side. So there are also cooling techniques in which it's going to be power is going to be generated. For this thermoelectric generator, no need of additional heat and other things. Whatever the heat which is excess from this solar PV panel, that is taken into that consideration to additional power. How this copper, the PV panel, so over which they're fixed in solar PV, thermoelectric generator. This thermoelectric generator is cooled with some copper copper pipe or cooling mechanism. So in the cooling pipe or cooling pipe is having the different fluid and different orientation that also helps the overall system, the performance of combined the PV thermal system or tech integrated. So another the hybrid system where in which the thermoelectric model which is going to be fixed over here. Probably you can see these small circles. This the thermoelectric model which is going to be fixed. So this system which is used for this what you call it a micro scale heat and electricity generation for the hybrid solar collector chimney, the thermoelectric and wind turbine which is added. So where this section which is going to be wind turbine, it's combined system, it's a solar collector. Then bottom of the solar collector, this PV model is going to be fixed over here. So this also it's placed in a good journal. It is a chances for think it further for how the things can be worked out. So another the combinations which was a group of people which in Vellore Institute of Technology, they made the system what I told in a thermoelectric generator in the back side. They are used what you call that in graphite. How the graphite? So you can have a look. So it will be very interesting one. So here I was noticed there are many thermoelectric model they fixed over here where this cooling side they are fixing this graphite, the cooling medium they're fixing its graphite. It's also recently published in SCA journal. So that's what I like to share to you, so for your quick understanding. Then the complete set of what that group people in VIT they made it small setup. It is easy to what you call that uh, fabricate. So with some funding 2 to 3 lakh. So it will be the sources. You can also have look on this pictures where this instead of graphene you can go for any other cooling materials, any other what you call it low temperature materials, or it will be stored the heat in the backside of the thermoelectric. That also it is what you call it and giving some much attention. So that's what I said in the beginning somewhere. It's a 0.1% efficiency improvement. It's a great. Even in 0.1% cost reduction also it's a great as far as the research is concerned. Where these people are given the report, it was very interesting. Where what you call it and the F signals, where the F signal is giving what you call it and thermoelectric generator efficiency is better. So when it was shown where this TF, what do you call it, thermoelectric graphite at 800 watt per meter square solar radiation, where graphite at 700. But when it's working on high temperatures, so probably it is in cooling heating of thermoelectric that gives in a better efficiency. So it is a research output where this thermoelectric model and PV generator they are given in a very nice pictorial representation. The PV back side it is attaching with the hot side of the thermoelectric models, where the cold side which acting as a graphite. So this is a picture where in which the PV cell it's not going to affect its performance when you are keeping it in a very optimum temperature. But whatever the excess temperature which is generated in a PV models using it what do you call thermoelectric model, a thermoelectric generator, it gives additional electricity. That both electricity can be used to run your electrolysis of alkaline or PEM fuel cell. Where there's some pictures, so no need to discuss now. So let me skip it over here. Where this again the thermoelectric generator, I also worked on this some thermoelectric model. So one of my the next batch of my person is worked on this. You might be seeing this PV models over thermoelectric model is here, where this parabolic trap concentrator, it is concentrating solar radiations on this hot side of the thermoelectric model, where this cold side is used what you call it in water, cold water. So now after 24 almost 10 years, after 10 years, people are using what you call it an observer plate, the different cooling materials. So cooling material it helps to improve what you call it a thermodynamic efficiency of thermoelectric generators. So there is also some work which improvement of performance improvement of solar thermoelectric generator based on the phase change material and its heat transfer enhancement. It is a lab scale. It's at your home you can do small experiment here. They taken what you call it in paraffin wax here, and they made it in one data logger, one computers. So where this infrared radiation, it is acting as radiation for what you call the to run your thermoelectric generator here. This what you call it in pink, sorry, is saffron color. It's a thermoelectric generator which is happening. So where this it is in the T1, it's a hot side. Where T1 is cold side, it is having with the paraffin wax. Now it is connected with all the setups, small setup. It's connected with what you call a data logger. So you can take the readings, how it is going to be happen. So what I think I'm coming to near to the conclusions where this prospect and future research in the direction of green hydrogens. Some electricity, it is a known factor, is generated from solar, wind, biomass, ocean thermal, and that catalyst, even in a catalyst, they're searching for newer catalyst, what low cost catalyst and high performance catalyst. So that can also used for what you call it in its low and high acidity and long stability. That is in the catalyst area, where the electrolyte, it's a breaking freshwater limit. So freshwater is supposed to be in a limited. So that's what even in Dr. Renan Nauni sir, its own is in the levelized cost of hydrogens, that everybody using electrolysis, then it's going to, there is no water for even in that human being or animals or living organism. It's very difficult. So breaking the freshwater limit also, it's an electrolyte and value added to the product and utilization of the wastewater. These are the things where this next generation green hydrogen is coming into the picture, where the complementary of the coupling and reduced investment optimization efficiency on the electricity in the green hydrogens. So this area can be the next generations, where the next generation of the fuel, it's known, it's factors and green hydrogens. Hope we can have things at the same pictures, but it's in different the presentation in which it was mentioned here. Then electricity, where it's from wind, tidal power, photovoltaic or solar things. Instead of electrolysis, we can use for the steam deformation method also. Solar steam deformation method, it gives better efficiency breakthrough than probably this candidate of this electrolyzer is going out. The steam reformation is coming to the pictures, where the catalyst is components here, where it is an electrolyte is component, 3 component. So it was mentioned in a different aspect. So even in this, what do you call that, in the future research on thermoelectric performance, I didn't give some fundamental slide which was missing in this presentation. So tomorrow, let me give my presentation slide on this thermoelectric components and how that fabrication is happening. So that time probably if I say this slide and 67, it will be more appropriate. So it was prepared on yesterday, so I could not find a time because other commitment. So tomorrow presentation, let me give what you call it in complete details connected to this thermoelectric performance enhancement, which helps to increase the green hydrogens boosting and other things. So I like to give what you call it in something also over here, the closing before my sessions, the state of art in solar thermal system integrated thermoelectric as reviewed, and the advances in solar photovoltaic cell and add-on system using thermoelectric generator with PCM also we discussed. Then solar hydrogen generation technologies we discussed. Then cost reduction and efficiency enhancement on green hydrogens we always focused. Then green hydrogen potential using solar thermal and photovoltaic were discussed to meet the requirement as per this National Green Hydrogen Mission 2030. So I like to give what you call it in my sincere acknowledgements here now also. So national what you call it in ANRF, it is in self earlier, it's now it's an ANRF. They given some support for us to study something on the solar PV thermoelectric and its performance. Where this SERP now it's in ANRF, they are also given some support. Ministry of New and Renewable Energy, AICTE. So probably we should give thanks to them for providing an opportunity to us. And my Tamil Nadu State Council for Technology, when my initial state, they given my seeding money. So I also acknowledged where the Karnataka State Council also is given some support, some minor project, where this Kerala State Council also given some support, where the Karnataka State, then that's all from my side. I'd like to have thank for this session one. If you have any questions, then let me. eh, It's a pleasure to answer. So I finished almost before what you call that in 30 minutes. You have any questions? Sir, if you have any questions, you can ask me. Otherwise, yeah, thank you, sir. Thank you, Professor, for your compliments.
Sir.
Yes,
Good evening, sir.
Professor, good evening.
Sir, one question I have.
Yes, sir. Yes, sir.
In the lab, suppose for research purpose, so what should be the rating of the thermoelectric generator if somebody want to do research in the lab?
Thank you. So actually, thermoelectric generators, it is manufactured very famous company in Japan. It's Himatsu. Himatsu, it's technologies I know. They are giving what you call that a 20 watts capacity thermoelectric model. It's very in a very handy shape. It is what you call that a 5 centimeter into 5 centimeter length and width. What you call that, and then thickness. It's mostly in 5 mm to 6 mm. It's very compact. So you can also try. That's what in the figure when I saw the backside of photovoltaic cell. So almost 10 PV, sorry, thermoelectric model there attached it. See, each model might be in a 10 watts or in a 20 watts. See, if the 10 model is there, 10 into 20, it's a 200 watts. Even in PV panel, it's a 200 watts. But this small hands, it's giving what you call the 10, it's a 20 watts. It's very compact in size. So that also it's available even in the Himatsu, wherein HIZ from an US, then one Thermionic company from China. So don't believe these China people. Sometimes they used to cheat us. HIZ, it's in America. It's the best one. That's my understanding is concerned. My experience is concerned.
Okay, thank you, sir. Thank you very much.
Thank you, sir. Thanks for your interactions.
Professor, this is Dr. Eswaramoorthy from Tamil Nadu.
Yes, sir. Yes, Professor.
Professor, is there any maximum temperature and minimum temperature, the cold side and hot side?
Exactly.
Is there any
Yes,
range,
Professor? Yes, sir. Yes, sir. Actually, that when the manufacturer they used to what you call the term while giving the performance curve or performance parameters, they clearly mention you have to operate your thermoelectric models at this medium temperature or low temperature. When keeping in the some temperature limit at hot side, then temperature at the cold side there is no limit. So when the temperature gradient is going to be decreased, then there is no power. The one advantage is here in thermoelectric model, even 0.1 degree centigrade difference is come. This thermoelectric generator is giving what you call that and some amount of electric what you call it and the voltage. So that's what it's a great advantages in thermoelectric model. So 0.1 degree the temperature of hot water, we will also get an electricity, but hot water cannot produce a steam. The steam is having the high temperature. So that's what it's more advantages in this system. It's high reliable. So actually I could not bring that particular slide. Otherwise I missed it in the opening slide. So tomorrow let me give the comprehensive literature about thermoelectric. It is most attractive technologies. So even in what you call it, there has some limitation. That limitation is coming out now. Once it is commercialized, so it is going to feed your IC engines. One, the temperature difference is maintained, thermal management is maintained, and both hot side and cold side, it's going to generate in a better efficiency.
Thank you, Professor. One of my scholars is working in this area. I will contact you for further reference.
No,
Thank
no
you.
problem, sir. No problem. Most welcome. Most welcome. I'm ready to support.
Thank you.
Thank you, President. So, any other questions? Then let me say what you call it and things about the reflective journals. So I was committed. We shared it today by email. The reflective journals, whatever the understanding you done from the day one, as on today and tomorrow also. So it can be what you call the fill it up by typing the matter. It's good, not on the handwritten. So it will be. It can be submitted. So in future demand by an AICTE officials. So we have to submit all these records of the reflective journal. What you understand from this, what you call the 10-hour online FTP. I really appreciate all the participants who are joined on time and beyond what you call the 10 interacting with the speakers. It shows your enthusiastic and what you call it and the commitment on your things. The attendance, we are facing some server issue problem. We will upload whatever the attendance which is available with us in the Google Meet report. We will upload it before or tomorrow. That reflective journal, so you can take your time by Saturday, by Sunday, please you can submit. So once that's what from my side. So it is a maximum. Don't write maximum. Uh, 3 pages, limited to the 2 pages, it's enough. If it's single page with your consigned things, that is also very things where we like to go for it one. Then tomorrow, once the program, what you call it, and things are over, validatory is over, with the feedback to your login ID, so you can give feedback about the program. So that also what you call it a mandatory for downloading your participation certificate. Once we what you call it and uploaded all the attendance and the test also, I already mentioned it is an objective type. It is a basic questions and two numerical problems. So we are purposely added to what do you call the 10 that check the attendance or what do you call the 10 things of our my participant. Don't think and otherwise. So it will be 25 question objective type. Then each question is having a 4 marks, so it will be in 100. So once the score also will be displayed at your end. So we are also having a discussion with the whoever is coming in a better scores. We like to keep something. So from our some impress money, so to give motivation to my participant. That's all. So we are also like to expect your all the participants on your presence once that what do you call it and offline any opportunities is come in the offline mode, please you can visit and have a darshan of pada also. So that's what I like to convey in this note. If you have any other further questions, we are closing our sessions. I think 20 minutes before.
Sir, excuse me, sir.
Yes, sir. Yes, sir. Please.
Sir, I'm Dr. Varun from NIT College, Greater Noida. Sir, actually, I want to start some research in the hydrogen field. So, sir, I just want to know, sir, because if we go in the experimental zone, it takes lot of area and lot of equipments and things like that. So it is a very costly affair. So, sir, is there some experimental setup or rig is available where we can actually go and just do the experiment?
No, so on the experiment setup, whatever it's shown by the previous speaker, Dr. SivaReddy, it is already, I think that setup which is available over there. It is what you call it in some there were many components, many problems which is associated in this particular the hydrogen generation dispensing unit. As a PhD scholar, my advice: don't take a big problem, take a very simple problem and you can 2 to 3 objectives and make it is for your academic grade, so academic credit, that's what you like to have some publications, so then you can proceed. But don't think you can do what you call that, and after your PhD you can start your own startup. But you won't get your PhD further, don't keep, keep your leg overstrength, so it will be problem for you.
Okay, sir. Okay. Thank you, sir.
Okay.
Sir, when is the test time tomorrow?
So tomorrow, once the validatory is over, so we are going to share that test link to your WhatsApp group as well as a chat box as well as an email. We are
Okay,
giving
and tomorrow
1
timing
hour.
of our session is at what time?
So tomorrow the session will start at 2 o'clock. So the speaker from UK will join at 2. So
Okay.
I request all your presence before 2. It will be convenient to say that we are very eager to wait for that professor talk. That will be give moral, what do you call it, and a good ambience to him, the speakers. That's what my expectations.
Okay, sir. Okay.
Yeah, thank you. The feedback will be served to you in your email ID. So at the 9 o'clock, sir. Slope Bharati.
Hello.
Yes, ma'am.
Hello, sir. I want to ask you about whether can you list out some virtual labs for the hydrogen production system?
Virtual lab.
Virtual labs are available.
No, ma, no. I don't have any, what do you call it, knowledge about the virtual lab on this hydrogen production systems.
Okay, sir.
Can I answer this question?
Yes, Professor, please.
Sir, actually, madam, there is no virtual lab, but there is a physical lab in IIT Mumbai. Pratibha Sharma, Dr. Pratibha Sharma, she is the overall in charge of the Center of Excellence in Hydrogen, and she is having the lab also.
Yes. I know some NPTEL courses available online.
NPTEL course, and they have taken the lab sessions also in that.
Okay. Thank you, sir. Thank you.
Thank you, Dr. Malik, sir.
Thank you, sir.
Sir, Professor Eswaramoorthy, sir.
Yes,
Hello.
sir. Yes, Professor.
Sir, this is Dr. Rangarao from Vignan University.
Ah.
Sir, actually, I work more algal biotechnology, sir, microalgae. Actually, I want to start something green hydrogen production from the algal sources, sir. Is there any help I may get who can able to work on this one?
No, algae-based green hydrogens. So it is a biomass route, right?
Yes, sir. Yes.
Biomass route, please. You can. I don't have any idea about. Otherwise, you can check with National Institute of Bioenergy. It is in Kapurthala. So
Okay,
probably
sir.
that the scientist might be giving you some insight.
Okay.
Thank you, Professor. Thank you. National Institute of Bioenergy.
National Institute of Bioenergy, Agartala.
Kapurthala.
Okay.
Rajiv, am I right?
Kapurthala.
Yes, Professor. Yes.
Okay. Sir, tomorrow at what time you will share the link for this?
Sir, 2 o'clock session we will share. So 1 o'clock, sir.
No. Is there any tomorrow any like a questionnaire where we need to fill anything during the section?
Questionnaire.
Any
Questions will be at 7 o'clock. Sharp at 7 o'clock.
So you mean evening, sir? You mean
Evening 7 o'clock.
Okay.
Don't worry about it. It's only the basic level examinations. Basic level, what do you call that in questions?
Okay. So this reflective journals, no, sir. We just fill only one page and I share to you, sir. Is it?
Yeah,
right?
no problem. Whatever you understand, you want to respond that, it will be fine for us.
Oh, thank you, Professor.
It's a record to submit to the AICTE office in the soft copy. If they need something, they will refer it.
Thank you. Thank you.
Sir, we have to submit one page, or what we have to submit
The reflective journal, there were some questionnaires in which you have to respond it. So that we already shared in an email. Probably you might be received it. Please, you can check it out, sir.
Okay, sir.
Okay, so if no questions, shall we close this day 5 session 10?
Okay, sir.
So please could you repeat the submission date for the report?
Which report, madam?
Journal report, journal.
Report.
Yeah,
Okay, report. The reflective, the journal report, the format we already shared. So in which there are you have to fill in the blanks. Write something about this, what you call that, and workshop, the FTP program, and what you understand, what you like to carry forward. That's all it's mentioned on the particular sheet. And insert your signatures and put your, what you call that, and convert in a PDF, and save the file name as your name. So it will be easy for us to locate your reflective journal report. Is it clear, ma'am?
So I just wanted to know the submission date. When do we do it and how do we do it?
No. You take up to Sunday. Sunday, we are giving an enough time. Up the next day, the 15th of December, we are giving a time.
Yes,
Is it
sir.
okay?
Okay.
How
Do we
many
mail it
words,
to you?
sir?
Sir,
Do
silent.
How many words the journal
Sir,
report?
you limit your the report within the 2 pages.
Okay, sir. Thank you.
Sir, do we mail it to you?
Yeah, you mail it to me. Otherwise, there will be, what you call that, in Google Drive. Sorry, Google Drive we shared with you, in which you can put it your report with your name. Thank you, ma'am. So, shall we leave today? So we are thankful all the participants for your time and spending with us. So we'll join tomorrow at 2 p.m. So I will share you the link tomorrow link at 1 o'clock. Thank you, sir. Thank you, Ananda. Now the network center stop recording.